Force. Force is that which enables us to do work. For example, if we want to open a door, either we push or pull it. A drawer is pulled to open and pushed to close. Therefore, force is said as push or pull. Effects of force. Force can make a stationary body in motion. By using a force, you can move a ball, stop a moving body, change the direction of a moving object, change the speed of a moving body, and can change the shape and size of an object. Force can stop a moving body. For example, by applying brakes, you can stop a cycle or a vehicle which is in motion. Force can change the direction of a moving object. By applying force, that is by moving handle, you can change the direction of a running bicycle. Similarly, by moving steering, the direction of a running vehicle can be changed. Force can change the speed of a moving body. By accelerating, the speed of a running vehicle can be increased. Force can change the shape and size of an object. By hammering, a block of metal can be turned into a thin sheet. By hammering, a stone can be broken into pieces. Types of force. Forces are of two types: balanced force and unbalanced force. Let us understand it with the help of an activity. Take a wooden block on a horizontal table. If we apply a force by pulling the string X, the block begins to move to the right. Similarly, if we pull the string Y, the block moves to the left. But if the block is pulled from the both sides with equal forces, the block will not move. Such forces are called balanced forces. Balanced forces do not change the state of rest or motion of an object. Thus, the balanced force is zero. Squeeze a rubber ball between your palms. What do you observe? The shape of the ball gets changed. The force applied on the ball is equal and opposite, so the resultant of this force does not move the object. The objects get deformed as long as the force is applied. This is a temporary deformation. Here, equal and opposite forces act on a body and the body does not move. So we can say that the body is in equilibrium. Body. We can also state as balanced forces acting on an object. The resultant of balanced force is zero. Unbalanced forces. Let us consider a situation of two opposite forces of different magnitudes on the seesaw balance. A boy moves in forward or backward direction on the seesaw balance. We can observe in each case the resultant of these forces is always greater than zero. Hence, the force is said to be unbalanced. Thus, unbalanced force is explained as when we apply a force on an object and the object moves, that is, resultant is not equal to zero, the forces are called unbalanced forces. An object in rest can be moved because of applying unbalanced forces. Laws of motion by Galileo Galilei. According to Galileo, object moves with a constant speed when no forces act on them. This means if an object is moving on a frictionless path and no other force is acting upon it, then the object would be moving forever. That is, there is no unbalanced force working on the object. Let us explain with the help of an activity. Take two equal size cardboards, place it against each other that they make equal inclination with the table. Assume that both surfaces are frictionless. Now take marble and release it from the inclined plane of the left side. You notice that the marble rolls down and moves up on the inclined plane on the right side. Now think about how far it moves along the second plane. Well, the slope of both the surfaces are same. Hence it moves the same height from which it is released. Now decrease the inclined plane on the right side and release the ball again. What do you see? It traveled large distance to reach the original height. We can keep on doing it, but what does happens when the slope of inclined plane eventually reduces to zero? That is, makes a horizontal. The marble will continue to travel forever until it reaches its original height. But it is impossible because all ideal conditions should be zero. Mass and inertia, the property of an object because of which it resists to get disturbed its state, is called inertia. In other words, inertia is the natural tendency of an object which resists the change in the state of rest or motion of the object. Inertia of an object is measured by its mass. A heavy object has more inertia than a lighter one. Let us explain with the help of an activity. Take a 5 rupee coin on a stiff card covering an empty glass tumbler standing as shown here. Give the card a sharp horizontal flick with the finger. If we do it fast, then the card shoots away, allowing the coin to fall vertically into the glass tumbler due to its inertia. The inertia of the coin tries to maintain its state of rest even when the card flows off. Newton's second law of motion. Before going to discuss the second law of Newton, first let us know about momentum. The momentum of a body is defined as the product of its mass and its velocity. That is, P is equal to mv. Momentum is a vector quantity. The direction of the momentum vector is the same as the direction of the velocity vector. The SI unit of momentum is kilogram meter per second. The second law of motion states that the rate of change of momentum of an object is proportional to the applied unbalanced force in the direction of force. Suppose an object of mass m is moving along a straight line with an initial velocity u. It is uniformly accelerated to velocity v in time t by the application of a constant force F throughout the time t. Initial momentum of body P1 is equal to mu and final momentum of body P2 is equal to mv. The change in momentum is directly proportional to P2 minus P1 is equal to mv minus mu is equal to m into v minus u. The rate of change of momentum is directly proportional to m into v minus u by t. F is directly proportional to m into v minus u by t. F is equal to km v minus u by t is equal to kma. Here a is equal to v minus u by t is the acceleration, which is the rate of change of velocity. The quantity k is a constant of proportionality. The SI units of mass and acceleration are kg and meter per second square respectively. The acceleration a of a body is parallel and directly proportional to the net force F acting on the body, is in the direction of the net force and is inversely proportional to the mass m of the body. Newton's first law of motion. Any object remains in the state of rest or of the uniform motion in a straight line until it is compelled to change the state by applying external force over it. According to the Newton's first law of motion, if a body is in rest, then it will remain in rest unless unbalanced forces compel it to move. Second, if a body is in motion, then it will remain in motion unless unbalanced forces compel it to come in rest. This means all objects resist in changing their state. The state of any object can be changed by applying external forces only. Newton's first law of motion in everyday life. If an object is kept on the ground at a certain place, then it will remain on the ground unless a force is applied to move it. You fall backward when a scooter starts moving suddenly. It happens because you and scooter both are in rest. But as the scooter starts moving, your leg starts moving along with the scooter. But rest of the portion of your body has the tendency to remain in rest. Due to this, you fall backward if you are not alert. When you apply brakes suddenly on a moving scooter, you fall forward. This also happens because of the theory of Newton's first law of motion. When the scooter is moving, the body in it also is in motion along with the scooter. But when you apply brakes, the speed of the scooter decreases suddenly or scooter comes in the state of rest suddenly. In this condition, the body of the person that is in contact with the scooter comes to rest, while rest of the part of your body has a tendency to remain in motion with the same speed. This causes the person to fall forward if he or she is not alert. Before hanging the wet clothes over laundry line, usually many jerks are given to the clothes to get them dried quickly. Because of jerks, droplets of water from the pores of the clothes fall on the ground. It happens because when suddenly clothes are made in motion by giving jerks, the water droplets in it have a tendency to remain in rest, are separated from clothes and fall on the ground. When a pile of coins on the carom board is hit by a striker, coin only at the bottom moves away, leaving rest of the pile of coins at same place. This also happens because of the theory of Newton's first law of motion. When the pile is struck with a striker, the coin at the bottom suddenly comes in motion because of the force applied by striker, while rest of the coin in the pile has a tendency to remain in the rest, and they vertically fall on the carom board and remain at the same place. Third law of motion. There is always an equal and opposite reaction, or the forces of two bodies on each other are always equal and are directed in opposite directions. Let us explain with the help of activity. Let us consider two spring balances connected together as shown here. The fixed end of balance B is attached with a rigid support like a wall. When a force is applied through the free end of spring balance A, it is observed that both the spring balances show the same readings on their scales. It means that the force extended by spring balance A on balance B is equal but opposite in direction to the force exerted by balance B on balance A. The force which balance A exerts on balance B is called the action, and the force of balance B on balance A is called the reaction. This gives us an alternative statement of the third law of motion. That is, to every action there is an equal and opposite reaction. Let us take another example. Take a big rubber balloon and inflate it fully. Tie its neck using a thread. Also using adhesive tape, fix a straw on the surface of this balloon. Pass a thread through the straw and hold one end of the thread in your hand or fix it on the wall. Now remove the thread tied on the neck of the balloon. Let the air escape from the mouth of the balloon. Observe the direction in which the straw moves. Air exerts a force, that is action, to move balloon, that is reaction. The air exerts an equal and opposite reaction force on the balloon. When a gun is fired, it exerts a forward force on the bullet. The bullet exerts an equal and opposite reaction force on the gun. This results in the recoil of the gun. Since the gun has a much greater mass than the bullet, the acceleration of the gun is much less than the acceleration of the bullet. Conservation of momentum. Suppose two objects, let's say two balls A and B of masses MA and MB are traveling in the same direction along a straight line at different velocities UA and UB respectively, and there are no external unbalanced forces acting on them. Let UA is greater than UB and the two balls collide with each other as shown here. During the collision, which lasts for a time t, the ball A exerts a force FAB on ball B, and the ball B exerts a force FBA on ball A. Suppose VA and VB are the velocities of the two balls A and B after the collision respectively. The rate of change of its momentum, or FAB, or action, during the collision will be FAB is equal to MA into VA minus UA divided by T. Similarly, the rate of change of momentum of ball B is equal to FBA, or reaction, during the collision will be FBA is equal to MB into Vb minus Ub divided by t. According to the third law of motion, Fab is equal to minus Fba. Therefore, Ma into Va minus Ua by t is equal to minus Mb into Vb minus Ub by t. Cancel t each other, we get MaVa minus MaUa is equal to minus MbVb plus MbUb. Therefore, MaUa plus MbUb is equal to MbVb plus MaVa. Since MaUa plus MbUb is the total momentum of the two balls A and B before the collision, and MbVb plus MaVa is their total momentum after the collision, we observe that the total momentum of the two balls remains unchanged or conserved provided no other external force acts. The law of conservation of momentum states that the total momentum of the two objects is unchanged or conserved by the collision if there is no external unbalanced force acting on them.